Hey, what's up, kids? How's everyone doing today? So, this is Mr. Edwards. I'm Mr. Pepic. Char!
Mr. Pepic is just joining us in my class today, and we're just going to do two street conversion factors. That's what we're doing today.
That's right. And Mr. Edwards is going to join me in my class today as we do a couple of conversion factors. So, I miss Mr. Edwards so much. We taught next door to each other for years, and yeah. So now I was like, hey, dude, let's do a listen. I said, let's do a lesson together, and he's like, love to. So we're gonna teach conversion factors together.
Get this ready. Get this ready.
Take out your periodic table, take out your calculator, and take out a pencil or pen. Thank you, Mr. Edwards.
No problem, right. Mr. P.
All right, and that is my boy's going to be running through, and his boy's running through as well.
Walker's pissed right now. They know. Walker's my son. He's 3 years old.
Yeah.
Sorry, dude.
All right, ladies and gentlemen. So what Mr. Edwards just is showing, and it's what you see on the screen here as well. This is something that I created. It's called a mole map, ladies and gentlemen. A mole map. And there's the moles right here. And it's going to guide us through this. It's going to guide us through our conversion factors, because we're going to start using multiple conversion factors. Up until this point, ladies and gentlemen, we've used one conversion factor. But starting today, we're going to use two conversion factors. So as we were saying, up until this point, ladies and gentlemen, you have only used one conversion factor. Like you've only used molar mass, okay, or molar volume or Avogadro's number. So far we've only used one conversion factor. I see your hand, Mr. Adams. Hold on one second. But today, just so you can anticipate what we're doing, we are going to be doing two conversion factors. So we're going to have a conversion factor and another conversion factor. And the only thing you're going to have to remember is that we multiply the numbers on the top and we divide the numbers on the bottom. But let Mr. Edwards jump in here, ladies and gentlemen. What did you want to say, Mr. Edwards?
Hey, so I think you just answered my question. My question was, are the conversion factors those things that go inside the parentheses?
That they are, my friend. These are the conversion factors. And we know three conversion factors up to this point. Do you know the names of any of the conversion factors, Mr. Edwards?
I know them. One of them is called the molar mass.
Molar mass, excellent.
Another one is called the molar volume.
Excellent.
And another one's called the Avogadro's number.
I feel like you were cheating. I really feel like you were just looking at the screen as I was circling, but I'm gonna figure out that you were. I'm gonna guess that you were doing that on purpose. You knew the answers. So that's right. We have three conversion factors that we've learned. We've learned molar mass, we've learned molar volume, and we've used Avogadro's number. Molar mass, that was used when we wanted to find out the amount of grams, okay? When we're working with grams, that's molar mass.
You get that, wait a second. You get that number from the periodic table.
Yes, excellent. Periodic table, molar mass. Avogadro's number, let me do that again. Molar mass, we are going to get from the periodic table. And then the next one, I'll put this one in blue for us. Actually, you know what? Let me put it in green. You know what? Let me just start over here.
Excellent choice.
You know what? Maybe I will use yellow on this one. All right, yellow. That doesn't work well, but that's all right. So the molar mass uses the periodic table. And then Avogadro's numbers, ladies and gentlemen, which is right here. This is Avogadro's number. This tells us how many individual pieces of stuff we have, like how many atoms or molecules. Where do we get that number from? Mr. Edwards, where do we get that number from?
We get it from the mole roadmap.
Yeah, but what's the number? Whereas molar mass, we got from the periodic table.
My fault. So there's 6.02 times 10 to the 23rd things per 1 mole. But I think we're going to be talking about like atoms and particles. So if the question says how many atoms or molecules, we should probably use that conversion factor.
That's right. That's our conversion factor right there. We don't even have to look for it. What if we're going to work with molar volume? When we're working with molar volume, what number And where do we get the number for molar volume of a gas? Yes,
I
Mr. Edwards.
I can read 22.4 liters per mole. I see it right there.
I would have made it more difficult if I could have, but I chose to make it easy, Mr. Edwards. That's right. So molar volume, it's right there. Avogadro's number, let me change the color to green. It's right here. And molar mass, yep, you know it. You have to go all the way to the periodic table right over there. That's where we get that number from, which is why there's no number right there. And everything is per mole.
Oh,
So
question.
up until this point, I'm gonna be a little serious. Up until this point, kids, we've used one conversion factor right here. So what have we learned how to do? We've gone from grams to moles and moles to grams. And we used this street. I'm gonna be calling it a street. And so is Mr. Edwards. And he's also gonna call it a conversion factor. And we'll say, how many streets are you gonna take? A street, that's right. Did I spell it wrong? No. So this would be one street. So if we converted grams to moles, going from grams to moles, we'd use the molar mass. And if we were gonna go from moles to grams, we'd use molar mass. Do you guys see how that works? Mr. Edwards,
Oh my gosh.
blown away. Let's do the next one. We also learned how to go from molecules to moles. You didn't realize it. Let me get to this street. But we were using this street right here. And it took one conversion factor. We had what we started with, then Avogadro's number, I'll put A in, and then our answer, right? We used one street. We started at molecules to go to moles. We go this way. We also did molar volume, ladies and gentlemen. And molar volume was another street. What's the name of this street right here, Mr. Edwards?
You said it best. Molar volume.
That's right. So we're going to call this street molar volume. Mr. Edwards, what is the name of this street right here? What's the name of that street?
Oh, Avogadro. That's Avogadro's number.
Yes, Mr. Edwards. Lastly, what's the name of this street right there, Mr. Edwards?
Looks like you're circling it.
What is it?
Molar mass.
Absolutely. So, ladies and gentlemen, we have learned three conversions: molar mass, molar volume, and Avogadro's number. But today, we're going to do two streets, which means instead of starting at mass and going to moles, okay, I can hear the excitement, Mr. Edwards. What do you predict we're going to do?
So you're telling me that this map
Yep.
helps me convert from one unit to another unit, and each road represents only one conversion factor?
You know what? I love that you're with me because you're really just making this awesome. That's right. This right here, that would be the parentheses. That would be the parentheses. This would be the parentheses.
I just want to say thanks for coming to my class, Mr. Pepic. This has just been really great to have you here as a guest.
Well, I would actually like to thank you also for being a guest in my classroom today, Mr. Edwards. What a treat. It feels like old times, you know?
Let's do a problem.
I think we're about ready, but let me start you off here very quickly. Kids, I asked you before, I would say start here and end, which is why I was very specific. Boom, it would take one street. But today, we're going to start at grams and we're going to end at volume. How many streets do you guys think it's going to take to get from mass all the way to volume? How many streets is it going to take? Mr. Edwards?
I'm counting, and it's going to take two streets.
It is going to take two streets. How many conversion factors, Mr. Edwards?
Well, since each street represents a conversion factor, that means we're going to take two streets. That's two.
Awesome. You know what's awesome? All of my students are just like you. They're thoughtful. They're just anticipating answers, and they're wanting to find out what this is all about.
All I got to say is my students are better.
You represent the best of my students, Mr. Edwards. So you want to work out a problem?
Yes.
Let's do it. All right, ladies and gentlemen, we are going to start example number one. Now you can see things are a little bit different. You're probably looking at the screen right now going, wowzers, looks like we have two conversion factors, also known as two, what?
Eats.
Good. Two streets, ladies and gentlemen. So the two
Hmm.
streets correlate to the two conversion factors. Okay, let's get going. First thing I ask you to do, please read the question. We have how many liters of carbon dioxide gas in 1.86 times 10 to the 24th molecules of carbon dioxide gas. So the first thing that we want to do is figure out what are we solving for? Where are we trying to go? What's our answer going to be? So what are we solving for in this problem, Mr. Edwards?
I'm here to answer questions. So if I'm reading the problem, it says, how many liters of carbon dioxide gas? So I automatically know that my answer is going to be some number of liters of carbon dioxide gas. Why did you write molecules, Mr. P?
Are we not? Did I mess up?
Yes.
Thank goodness that you're here, Mr. Edwards. All right, kids. So we're going to do liters then. Much better idea, Mr. Edwards.
Can I please just write a capital L instead of writing the whole word?
Yes, I love that idea. Let's just write an abbreviation for L, liters of carbon dioxide.
Thank
What
you.
are we starting with over here, Mr. Edwards?
Oh, okay. So if I'm reading the question correctly, it says
Wait,
how
wait,
many.
wait. Let me ask the question. Kids, what are we going to start with in this? All right, Mr. Edwards, feel free to answer.
I like that little Ed puzzle pause right there. So it's it says how many liters of carbon dioxide gas are there in 1.86 times 10 to the 24th molecules of carbon dioxide gas at STP. So I think I'm going to be converting 1.86 times 10 to the 24th molecules of carbon dioxide gas into liters of carbon dioxide gas.
Yep,
And
that was pretty fast. Mr. Edwards, what is the one word we are not allowed to abbreviate in chemistry?
we cannot abbreviate the word molecules because the word mole and molecules are two different things.
That's right. So you cannot abbreviate the word molecules, ladies and gentlemen. You have to write out the word molecules. So we know what we're starting with and we know what we're ending with. Nothing new has happened. So now what we want to do is figure out what conversion factors do we need. So I'm going to come over this way and we're going to take a look at our mole map. Okay, so this is called our mole map. Yes, Mr. Edwards.
So the map kind of works like if you look at the map and you know where you're ending and you know where you're starting, then you're not lost.
We are never going to be lost. So let's just take a look. Where are we starting? We're going to start right down here. So this is where we're going to start. How do you know? Because we're starting, ladies and gentlemen, with molecules. So this is where we're starting right here. All right, so I'm going to back that up. I don't want to circle that. I'm just going to go right here in blue. This is where we're starting. Now, where are we ending, class? Where are we ending? Yes, Mr. Edwards?
It's the L for volume, gases at STP.
That's right. We're going to end up here. Now, if we start down here at numbers of particles and we end up here at volume, how many streets will that be, ladies and gentlemen? How many streets will that take? Yes, Mr. Adams?
Dos en español.
That's right. Oh, you're just so fluent. Good job. All right, so yes, it's going to take two streets. Here is a street right here. All right, and then
that's the first one.
That would be the first street. And here is going to be the second street right here. I'm going to color code this so I can relate it directly to what we're doing on the periodic table or over in our problem. So there's street number 1 and street number 2. Here's my question. This street here, is it going to be a red street or a blue or a green street? So Avogadro's number, does it go here? Or is molar volume going to go right here where I'm circling? All right. Now, if we start right here and we're starting here, the first street we come to is Avogadro's number. So what you're going to do, and you'll do this on your paper, you're going to circle Avogadro's number to say, hey, Mr. Pepic, I know what we're doing. Then we have to put Avogadro's number in there. What is Avogadro's numbers, ladies and gentlemen? Well, let's work it out right down here. I'll put these two. What is Avogadro's number, Mr. Adams?
It is 6.02 times 10 to the 23rd.
6.02 times 10 to the 23rd, ladies and gentlemen.
And I think we're talking
Times
about
10 to the 23rd what?
I think we're talking about molecules. We want to convert the molecules into liters.
Molecules of CO2, ladies and gentlemen. All right?
That's right.
And that's for every 1 mole. For every 1 mole. All right? I don't like this line here. I'm going to erase it, kids, because it's a little bit too big. All right? There we go. Whoops. Oh, I'm going to pause this because my computer is...
Are you paused?
No. My computer's frozen right now.
Are you pausing recording?
I cannot yet. Hold on.
Do this example.
Okay, so sorry about that, ladies and gentlemen. Little technical difficulties, but we're back. That's right. So here it is. The first Avogadro's number, this is going to be our first conversion factor. Are we going to use conversion factor A or conversion factor B, ladies and gentlemen? Are we going to use conversion factor A or conversion factor B right here? What are we going to use? Mr. Edwards, what are we going to use?
Oh, this is a tough one. This is a tough one, but I got it. I got it. Okay. So I remember that since we're converting molecules, we need to cancel out molecules in the conversion factor. So molecules has to go on the bottom of the conversion factor, so it has to be B.
That's absolutely correct. It is B. And the reason for those of you that are just getting this, the purpose of this is so that the word molecules of CO2 cancels with the word molecules of CO2. That's it. And now, right now, we're at moles of CO2. So right now, we're right up in this zone. But we have another conversion factor because we don't want moles of CO2. We want liters of CO2. So this next conversion factor, right, which in theory would be green, what is the name of the second street or second conversion factor we're going to use?
Molar volume.
Yes, Mr. Edwards?
Molar volume.
Yes, molar volume. What's the number for molar volume, Mr. Edwards?
It's got to be the same number every single time, as long as it's a gas and as long as it's an STP. It's going to be 22.4 liters per 1 mole.
That's right, 22.4 liters of CO2, okay, for every 1 mole of CO2, or it's going to be 1 mole of CO2 for every 22.4 liters of CO2. Now the question is, which, and I'll put this one in green so that you can see the difference, because we're now on this conversion factor here. I'll erase that. We're now on this conversion factor. So are we going to use conversion factor A, or are we going to use conversion factor B, ladies and gentlemen? Now, I'm going to try and give you a hint. Right now, we're trying to cancel out the words mole of CO2. Which one are we going to use, Mr. Edwards?
It's got to be A.
Why do we have to use A, Mr. Edwards?
Well, A has the unit mole on the bottom, and we're trying to cancel out the unit mole. It also has the unit liter on the top, which is a unit we're trying to solve for.
That is exactly right, Mr. Edwards. So if you take a look, kids, moles of carbon dioxide is going to cancel out, leaving us liters of carbon dioxide, which is exactly what we want to do. And so at this point, all of our words cancel out, and that's the name of the game. Cancel out all the words, and when you have the letters that are left over that you want, then you're done. And remember, multiply all the numbers on the top, divide the numbers on the bottom. So let me work this one out for you, okay? I'm going to erase all of that so we can see. And let's take through and look right here. First thing we're going to do, 1.8, whoops, let me click in first. Okay, so I'll do a little parentheses. 1.86 times then, and remember, we use this button right here. Mr. Edwards, do you also use the Desmos?
I do not. I use this calculator right here.
Oh, okay. So my kids use an online calculator. So remember, that's the button we use for when we want to put an exponent. So I'll click that one time, okay? And then that's going to give us to the 24th, all right? Then I'm going to close my parentheses, and then we're going to multiply, and I'm just going to do it just like it is, times 1 divided by 6.02 times 10 to the 23rd. I'm going to click out, and I'm going to close my parentheses, because there's that parentheses. And then I'm going to start another set of parentheses. And what's that one going to be? 22.4 divided by 1, close parentheses. And that should be giving us our answer, ladies and gentlemen. Okay? So that's the answer. It's going to be 69.21, because we talked about going to 3 decimal places, but the kids I've been working with are really struggling. So I'm just going to limit it to 2 decimal places right here. And if you know how to round, perfect. If you don't know how to round, we'll just try our best and I'll be pretty lenient, okay? But this answer right here, kids, is going to be 69.21 liters of carbon dioxide. So as a quick review, I'm just going to go through this really fast, and then you take over, Mr. Edwards. All right. We had our first street, which is right here. There's our first street. This is our first street right here, molar volume. Then we had our second street, which is right here. Then our second street was Avogadro's number. We started with what we started with, and we ended with what we ended with, ladies and gentlemen. So that is how we got this problem done. You all are going to have this mole map. I highly suggest you either print it out or type it out later, or print this out, or just rewrite it, which would just take a few minutes to rewrite. All right, Mr. Edwards, I'm going to get this set up for you.
I'm the teacher now.
And I'm the student, ladies and gentlemen. So let's see how this works out. I've never been a very good student.
No, you
and
haven't.
He's never been. Well, you know what? I won't go there.
We'll call apples oranges. You know what I mean?
Okay, Mr. Edwards, let's see it.
All right, Mr. P, happy to do this question. So here's a new question. We got to make sure we get our stuff ready. We got a periodic table. We got our mole roadmap, and I got my pencil and my calculator. I'm all ready. So the question says, how many grams of O2 gas are in 67.2 liters of oxygen at STP? All right, students, let's use the mole roadmap so that we know where we're starting and where we're ending. The question's asking, how many grams of O2? So I know that I'm going to be solving for grams of O2. So when I set up my problem, I put an equal sign and I put grams of O2 at the end, leaving a space for a value. Let's read the question again. How many grams of O2 gas are in 67.2 liters of O2? So I'm going to be starting with 67.2 liters that needs to be converted into grams. So let's start with 67.2 liters of O2 gas. All right, students, now we're going to use our mole roadmap. It looks like we're starting with which unit?
I cannot see the map, Mr. Edwards.
You can't see the map? Okay, here we go.
There we go.
It looks like we're starting with which unit? Mr. P, can you answer?
Oh, yeah. So let's see. So you're starting at volume of a gas. So you're starting at 67 liters. So we're going to start up there at the big, where the balloon is.
Right there. We're starting right here at volume. We've got liters, and we want to convert all the way into what unit, Mr. P?
We want to go all the way to grams. That's right.
So all the way down here to grams. So, Mr. P, looking at the mole roadmap, how many streets did we take to get from volume, liters, into mass, grams?
Well, if I did this correct, if we start at volume, then we're going to have to take one street through molar volume and then another street through molar mass. I say 2 streets, Mr. Edwards.
That's right. I would agree with you. The first street is called molar volume, and the second street is called molar mass. So students, we know from the previous example that the molar volume conversion factor is written right here. We don't have to look anywhere else. It's 22.4 liters of gas per every 1 mole of gas.
Wait a second, Mr. Edwards. Are you saying we do not have to go to the periodic table to find the molar volume?
You do not have to go to the periodic table to find the molar volume. It is written right there for you. It's your job to figure out if the correct conversion factor is 22.4 liters over 1 mole, or if the correct conversion factor is 1 mole over 22.4 liters.
Perfect.
What would you say for our first conversion factor, Mr. P?
Well, for the first conversion factor, molar volume, I'm going to want to cancel out the liters in 67.2 liters. So I'm going to want to put liters on the bottom. And then I want to put the word mole on the top. So mole O2 on the top, liters O2 on the bottom. Because we want to cancel out that whole thing. And the numbers, I'm going to put the 22.4 with the liters.
I jumped again there. I apologize. All right, students, we just did it. We just converted from liters into moles. So if we did this conversion factor, 67.2 divided by 22.4, that'll let us know approximately how many moles of O2 we have. But we don't want to stop there. We want to get all the way to grams. So we're going to be using our second street.
Wait, are we done?
We are not done. We are not done with this problem.
Why not?
Because this is a two-street conversion factor, and that means we need to use two conversion factors.
I can't see. Where are we trying to go?
Oh, I think it's okay. Here we go. Ready? There we go. We're trying to get to mass right here. We converted from volume to moles, and now we want to convert from moles into mass. So the next conversion factor.
We have to take another street.
That's right. We have to take our second street.
Our second conversion factor.
That's right. So the second conversion factor tells us that there's the number of grams of stuff per 1 mole. There's not a number here for me to put in. What should I do? Where do I find the molar masses of the individual elements?
Where do you find the molar mass number? Isn't it on that paper?
Nope, it's not. It's not on this paper. The number of grams per mole is not written on the mole roadmap.
I'm going to have to go look somewhere else. Where's the only other place I've gone to look? I think we go to the periodic table, Mr. Edwards.
You said it, the periodic table of elements. You see, the periodic table of elements gives the molar masses of each of the individual elements. It's that number that's written right below the symbol for each element. So that number right there is the number of grams per 1 mole of that element. So let's take a look. What substance are we trying to find the molar mass for?
O2, oxygen.
That's right, O2, oxygen. So how do we find the molar mass, people? Well, here's a really quick review. We want to know how many atoms of each element there are in the molecule. So in this molecule, it looks like there's 2 atoms of oxygen. Since there's 2 atoms of oxygen, we need to take 2 times the molar mass of 1 oxygen. So that equals approximately 32 grams per mole of O2.
Or 32.00 grams per mole as well.
It does, 32.00.
What is that slash you have written there, Mr. Edwards? Because I'm not familiar with that slash next to the G moles. What is that?
Okay, good question, Mr. P. Good question, Mr. P. So just to let you know that if I write the units like this, grams per mole, that's the same thing as writing something like this. Grams per 1 mole.
Got it.
So if oxygen is 32 grams per mole, it could be written both ways. And in fact, this is the way that looks like the conversion factor. So maybe this is the way we should start writing it all the time.
I like it.
Huh. Great idea. Okay. So now the question is, am I going to be using conversion factor A, or am I going to be using conversion factor B?
So am I going to be trying to put the grams on the top or the grams on the bottom? I think we're going to use conversion factor A.
Good job. We're going to be using conversion factor A to put into our problem. So we have 32 grams of O2 per every 1 mole of O2. So students, we just used the mole roadmap correctly. And now all we got to do is use the calculator correctly, and we'll have our correct answer. So how do we use the calculator correctly? We have to know the order of operations. we're going to be multiplying by the numerators and dividing by the denominators. So this is how it looks when I put it into a calculator. Can you see the numbers there, Mr. B?
Oh, yes, I can. Perfect.
So let's start with 67.2. We're going to push the divide button because our next number is in the denominator, 22.4. And I like to push equals because it gives me the most amount of information. So I just push equals, and that says 3. All right, so it looks like 67.2 liters is 3 moles of O2. So I don't want to stop at moles, so I'm going to multiply by the next conversion factor. It looks like I'm multiplying by 32 because the 32 is in the numerator. So let's take that answer and multiply by 32. And we have our answer, people. Just slap a 96 on there and call it a day.
All right. So I think we're done. Mr.
Yeah,
Edwards.
that's the whole problem. We did it.
That we did, ladies and gentlemen. All right. So thank you. Oh, your screen is gone. Thank you very much, Mr. Edwards. And I will, that's it. I'm signing off. Oh, geez. Here we go. Charge. All right, kids. Have a good day. Take care of yourselves. If you do need any help, we're sitting here waiting for you to ask for assistance. Have a good day.